So in this exercise, we have two vectors x1 and x2 in R2, and we want to show that these two vectors form an orthonormal basis of R2. That's the first question. Okay, let's do the first question. Show that x1 and x2 form an orthonormal basis of R2. Vectors x1, vector x2, there are two vectors in R2. Is an orthonormal basis from R2. So recall that orthonormal basis is a set of vectors has norm 1, right? So we need to check these two conditions. The first condition, we will check x1 and x2 are orthogonal. So x1 is orthogonal to x2. And to check this, we compute the dot products in this case, or the inner products in R2, which is the dot products we have. So let's compute x1 inner product x2, or x1 dot x2 in our case. x1 is a vector cosine, right? x1 is a vector cosine of theta, sine of theta, and x2 is this vector cosine of theta, sine theta, dot product with this sine of minus sine theta, sine cosine of theta. So this is cosine theta times minus sine theta plus sine of theta cosine of theta, and this is 0. So the two vectors are orthogonal. This implies that x1 is orthogonal to x2. Second step we need to show is each vector has norm 1. So we just need to compute the norm. Compute the norm of x1 and norm of x2. Norm of x1 is by definition the square root of inner product with x1 with itself, or in other words, square root of x1 dot product with itself. This gives us square root of cosine square of theta, sine square of theta, and this 1, right? Root 1, which is 1. So norm of x1 is 1. Similarly, we can compute norm of x2. Is square root of the inner product of x2 times inner product with x2. So this is root of sine square theta cosine square theta with also 1. Therefore, two conditions are satisfied. Therefore, x1 and x2, they form a orthonormal basis for R2. Okay, we're done with the first question. So for any other question, we do similar. So if they give us in R3 three vectors in R3, we check they form an orthonormal basis of R3. Then the first step is we check they are pairwise orthogonal. So each pairs of vectors is orthogonal set, right? So two different vectors are orthogonal, and each vector has normal one. That's two things we need to check. Second question is, for any vector y in R2, write vector y as linear combination of x1 and x2. Yes, because x1 and x2 is a basis, this set of vectors is a basis for R2, so any vector y in R2 can be written as linear combination of the two vectors. Y equal to C1 x1 plus C2 x2. So now we need to find what is C1 and what is C2, two coefficients. So one way, the way we do usual way, which we usually solve the system equation, right? We have what is y? Vectors y1, y2, right? Just arbitrary vector in R2. Given to us a value of y1 and y2. C1 is just a scalar. X1 is a vector cosine theta, sine theta. C2 is minus sine theta and cosine theta. So we need to find C1, C2, right? Or in other words, solve the system equation. Right, we need to solve this system equation with variables C1 and C2 in R. Y1, Y2, C1 cosine theta, C2 sine theta, C1 sine theta, C2 cosine theta. Right, we have system of two equations. First equation, second equation. Two variables C1, C2, right? We can do Gauss elimination or anything. Examples. C1 and C2. Okay, but for this question, because we are working with orthonormal set, so there's another way. Yes, the first way is just do Gaussian elimination as we did just before from chapter 1. And second method, we just use a theorem we have in the class. So this is the theorem. Recall we have this theorem. V is an inner product vector space. So a vector space that is equipped with an inner product. We have a orthonormal set of vector in V, U1 to Un. We have a vector V is a linear combination of U1 to Un. And we will prove that the coefficient Ci will be the inner product of V with Ui. So in the book, they ask the condition that this set is not just orthonormal set, but it needs to be the basic. We don't need to use this condition, although the condition is still true in our case. We will use this theorem. Let me quickly prove it. So recall why this theorem is true. So we need to show that the coefficient Ci is the inner product of V and Ui, right? V is a linear combination of this vector. We will find all of these scalars. This is true because, say, V, the right hand side V with Ui. this right hand side, we need to compute this, and we will check it's equal to Ci for any I. So V is a linear combination here. Ui is okay, just the ith element in the set, the orthonormal set. By linearity of inner products, this gives us C1 U1 Ui plus until Cn Un Ui. Maybe we write one more step for plus Ci Ui Ui. So recall that this set of vector U1, U2, Ui, Un, they are orthonormal, right? These vectors are orthonormal. This means that U1, Ui, 2, Un. Orthonormal. This means that J is orthogonal to Ui for J different from I, right? So any two vectors in the set must be orthogonal. And the second one, we have norm of Ui is 1 for all I. We need the two conditions. So since U1 is also orthogonal to Ui, this inner product is 0. The first condition implies that the inner products of all Uj to Ui is 0. For all j different from I. The second condition says that the inner product of Ui with Ui itself actually square equal to 1, right? And we can do square root of both sides. So we get this one, inner product of Ui to Ui is 1 for all I. Okay, now replace this here. This one is 0 because the two vectors U1 and Ui are orthogonal. The same thing until Ui inner product with Ui. This one is 1. And Un inner product with Ui is 0 because the two vectors are orthogonal. So this gives us this one is C1 times 0 plus Ci times 1 plus Cn times 0, right? This one left hand side equal to C1 times 0 plus C2 times 0 plus until Ci times 1 plus Cn times 0. This is Ci. So we did finish the proof of the theorem. Actually, this is for all i's in the set from 1 to n. So we did prove this theorem. In the when we do the exam, we can skip. We don't need to prove the theorem. We can use it immediately. So what does that say? Let's say now we have, in our case, we have vector y written as linear combination of x1 and x2. Come back to the question. In our case, x1 X2 is an orthogonal set in R2, while in R2 is a linear combination of C1 and of X1 and X2 by the theorem above. Say theorem 1. Let's name it theorem 1. We have Ci, or say C1, is the inner product of white with X1, right? So it plays a role here. White is V in this case, UI is Xi, right? C1 is the inner product of Y and X1, and C2 is the inner product of white and X2. So we have C1 equal to, in our case, is the dot product Y1, Y2, Y1, Y2, and X1 is a vector cosine theta sine theta dot product. So it's Y1 cosine theta, Y2 sine theta. That is C1. And C2 is the dot product of Y1, Y2 with minus sine theta, cosine theta, Y1 minus Y1 sine theta, Y2 cosine theta. And this is what we need. In case this gives us the explicit value of vector Y, we can compute explicit values for C1 and C2 by replacing Y1, Y2 here. Otherwise, we have in the general case, any vector Y can be expressed as linear combination X1 and X2, where coefficients are given by this formula. Okay, and the last part of this exercise is verify that norm of Y equal to C1 square, norm of Y square equal to C1 square plus C2 square. So we have norm of vector Y. For the second equality, norm of vector Y is a norm of vectors Y1, Y2 in R2. So it's just square root of the dot product Y1, Y2, Y2. This is just square root of Y1 square, Y2 square, right? And we need to prove this for norm of Y square. So to square both sides, we have Y1 square plus Y2 square. Then the second equality, this prove this equality. Parseval formula is V is an inner product vector space U1 to UN is an orthonormal set in V. V is linear combination of these vectors. Then the norm of V is sum of Ci square. We need to compute the norm of V square. Norm of V square is the inner product of V with itself. V is C1 U1, Cn Un. Inner product with C1 U1, Cn Un. By linearities, we have C1 U1. Okay, we're gonna do this slow. So let's do it like this: C1 U1, with inner product with this term, the second term, and we do the same for all the other term, plus till Cn Un. And now we expand this one to this one, C1 U1, C1 U1 to C1 U1, Cn Un. That's the very first row, which is equal to this one because of linearity. You do it the same for the second row. I mean, on the mixed row here until the last one, Cn Un, C1 U1, Cn Un, Cn Un. The first row we have is equal to this row, equal to C1 square U1 inner product with U1 because of linearity, plus this one equal to C1 Cn U1 inner product with Un. This term is 0 because the two vectors U1 and Un are orthogonal. We do the same thing until the last row. We have Cn C1 Un U1 Cn Un. Because of linearity, the scalar we can take it out. So inner product Un. This one is 1. So all the term on the diagonal is 1. The rest are 0 because they are all orthogonal. So this gives us C1 square term 1 plus term 1 because the length of the normal vector U1 is 1, plus 0 plus 0 plus 0, 0 plus Cn square term 1 square, and this is the sum of C1 square to Cn square. Okay, this is the proof for the Parseval theorem. So in our case, we know that we know that normal V square is the sum of Ci square. In our case, we have vector y is of this form. By Parseval formula, we have normal vector y square is the sum of all coefficients square. In our case, C1 square plus C2 square. That's all. Therefore, we did prove the very first equality in the exercise. Here, this equality. And the other one, we already proved it from beginning. This is the definition. Yeah, so two things we need to know. First one is Parseval formula. The sum of all coefficients square is a norm of V square. For V is the linear combination of this vector, which they form an orthonormal set. Another theorem we use in this exercise is this theorem. Theorem 1. If vector v is linear combination of this vector, then the coefficient can be determined by inner product of v with each vector in the orthogonal set.